In this presentation, we'll discuss applications of rationalizability. This is Chapter 8 in your textbook. The first application we'll begin with is called the location game. It's also referred to as the hoteling model. So imagine there's a boardwalk, right? And the boardwalk can be divided into 9 subdivisions, 9 neighborhoods, 9 quadrants on the boardwalks. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now suppose there are 50 customers located at each position on the boardwalk. Right. So in position 1, position 2, position 3, etc. We have 50 people, 50 people, 50 people, etc. Okay? Now, also suppose there are 2 sellers. Let's suppose they're selling beer. They buy from the producer and they're able to sell the same beer, so identical product, they're able to sell that beer for a $1 profit. So maybe they get the beer from the manufacturer for $1, they sell it for $2, they make $1 profit. Something of that nature. Okay? They're told exactly what the price is that they're allowed to sell it for, so they're not able to compete with each other on price. These sellers are going to have to choose a spot on the boardwalk. So they're going to choose a location. And then, given that location, customers on the boardwalk will buy from the nearest seller. Okay, so customers are going to buy 1 beer apiece. So let's say 1 unit each from whoever's nearest, and in the event of a tie, sellers split a block. Okay? So for example, if one seller locates at block number 2 and the other seller locates at block number 4, the seller at block number 2 will get all of block 1, she'll get all of block 2, the seller at location 4 will get all of block 4 and 5, 6, 7, 8, 9, and they'll split block 3, right? If they had both located on block 3, they would also split block 3. Okay? And in fact, they would split all of the blocks, right? So if they both locate on the same block, every consumer is assumed to be equally distant from each seller. They're located shoulder to shoulder, side by side. And so they would split the consumers identically. So out of that 450 total consumers, 50 consumers per block, if they locate on the same block, they sell to 225 consumers each, make $225 profit. Okay? So that's the basic structure of the model. And what we want to think about is, where are these sellers going to locate on the boardwalk? Right? What location or locations are rationalizable? Okay, that's the primary question that we're going to be asking. Okay, so what locations are rationalizable? All right. So, when we think about rationalizability, the first thing that should jump to mind is rationality and the requirements of rationality. Okay, so rationality requires that, simply that the player does not adopt a strategy that's dominated by another strategy, right? Not strictly dominated by another strategy. Rationalizability then suggests that each player, under the common knowledge of rationality, each player knows that the other player is rational, and their other players in the game will not adopt dominated strategies, right? And so to start with, we have to identify, are there dominated strategies? Are there dominated strategies in this game? Well, let's draw this location again, this boardwalk again. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Location 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we ask the question, are there locations on this boardwalk that are dominated for either player, right? And so we can kind of start to look at some blocks. Is 3 block dominated? Is 8 dominated? Is 1 dominated? Etc. All right. Now I contend that the 2 endpoints of the boardwalk are dominated by the adjacent block. So I suggest that block 1 is dominated by 2, and by extension that 9 is dominated by 8 in the same way. Okay? Now, how do we see this? To see this, we have to show that 2 is always a better place to locate than 1, regardless of the belief about where the other player locates, right? So as far as rationality goes, we're allowed to believe anything we like about the other player. So we have to allow for the possibility that the other player adopts block 1 or block 2 or block 3 or block 4. We have to show that 2 is better than 1 no matter where the other player is expected to locate. Okay? So if you expect, so if the belief, so let's think about, I'm just going to call the belief of the player in question theta. So typically our notation would be the belief of player 1 about player 2 would be theta minus 1. I'm just going to say theta because these players are identical to each other in terms of their strategy space. So I'm just going to pick a generic player, one of them just arbitrarily, and say his belief is theta, right? So we're not going to actually number up players. I'm just going to have a generic player thinking about theta and in response his particular strategy, right? So suppose that your theta for the player in question equals 1, okay? Now, what is the utility of this player who has this belief? What is the utility of choosing block 1 under theta? Well, if theta equals 1 and you choose block 1, what's the utility that you receive? Well, you're going to get a tie for every single every single block on the boardwalk, right? Because you're both located in block 1, right? So if you think he locates in block 1 and you will locate in block 1, you're going to share everything. So utility is equal to all consumers, 450 of them, all right? 50 per block times non-block divided by 2. You split them in half, and so you get 225. Now, these are utility units, so I'm assuming you get $1 of utility per beer. So you could think of this person has linear utility in dollars. I'm making a simplifying assumption, okay? So each dollar that the person earns from beer is 1 additional utility unit. So we're abstracting from anything, any other more complicated preferences for the purpose of this exercise, okay? So, now, if instead this person who has belief theta 1 would try block 2, this is going to be the dominating strategy. If she tried block 2, what is her utility? Well, she's going to get all of blocks 2 to 9, right? She gets all those blocks, and the other person would get block 1. So if she thinks the other person locates in block 1 and she chooses block 2, she's going to get blocks 2 through 9 all to herself. So 8 blocks times 50 each. So she's going to get $400, right? And 400 beats 225, right? So 400 is the winner out of those two. All right? Now, what if theta is equal to 2? Well, if she locates at block 1, her utility is just going to be block 1, right? Because, the proceeds associated with block 1, because the other person's going to get all of blocks 2 through 9 because she's closest to those consumers. So, her utility is simply 50, right? Whereas the utility of adopting 2 under that particular theta, under the belief that she locates in block 2, is going to be 225. Right? Because if she believes the other player locates in block 2 and she herself locates in block 2, her expected utility is half of all the consumers, 225. And again, locating in block 2 is better than block 1. 225 is bigger than 50. Right? We'll think about the belief that theta is equal to 3. Okay, if theta is equal to 3, the utility of choosing 1 when the other player locates at block 3 is equal to, well, you're going to get all of block 1, right? So you're going to get 50. You're going to get half of block 2 because you're equally close to block 2 as the person located at 3. So you're going to get 1/2 of block 2. So you're going to get 75, right? But if instead you had located at block 3, you would have tied, if you had if I instead had located at block 2, that's the dominating strategy I'm trying to identify. Right? If instead I had located at block 2, and the other person, and the other person had located at block 3, I get the utility of both all of block 1 and all of block 2. So I'm going to get 2 times 50, which is equal to 100, which is bigger than 75, right? Now note, if I believe that the other person locates at block 3, I'm not saying that 2 is the best response. It's clearly not. I'd be much better off playing 4 than I would at 2. So we're not trying to say 2 is the best thing to do. What we're trying to show is that no matter what our beliefs are, 2 is always better than 1, right? So we showed at first that under the belief that the other player locates at block 1, 2 is better than 1. Then we said, well, what if the other person locates at block 2? Well, 2 is better than 1. What if the other person locates at block 3? Well, yes, indeed, 2 is still better than 1. And of course, if the other person locates at block 4, 2 is still better than 1 because 2 is closer to 4. So I'm going to get more of the middle between 2 and 4 than I would before. So in that particular case, if the other person locates at block 4 and I locate at block 2, I get all of blocks 1 and 2 and we split 3. If I had located at block 1, I would just get 1 and 2. And the other player would get 3 and 4. So I wouldn't get none of that block 3. And the same if the other person had located a 5, 6, 7, 8, or 9. Because 2 is closer to that number, it's always going to move the middle, the dividing line between the people I get and the people the other person gets, is going to move it a little bit to the right. Okay? So, by similar argument, locating at block 2, so the strategy is better than the strategy of adopting block 1 for all possible beliefs. Okay? And thus, 1 is dominated by 2, and similarly, 9 is dominated by 8 by the same argument. Just from right to left instead of left to right. Okay? So, 1 and 9 are dominated strategies. This does not require the common knowledge of rationality. We don't have any restrictions on our beliefs about the other player. A rational person does not locate at block 1 or block 9 because there's another strategy that is available, the adjacent block, that is always better. It doesn't mean that adjacent block is the best strategy. It means that you would never do the dominated strategy. There's always a better alternative to it. So it doesn't say that 2 and 8 are good things to do. It says that 2 and 8 are always better than 1 or 9, so 1 or 9 is never going to be played. Okay. So that's what rationality buys us. Common knowledge of rationality buys us that each player knows the other player will not play 1 or 9. Okay? So we're trying to find the rationalizable set of strategies. The common knowledge of rationality suggests that 1 and 9 are not rationalizable. Right? They're not rationalizable. They're dominated for both players, and they both know that about each other. So it's as if 1 and 9 on our boardwalk don't even exist. So we can think of the boardwalk game, since 1 and 9 are no longer feasible locations, we can think of a boardwalk game in terms of locations. Of course, the customers are still in 1 and 9, but we only have to worry about players locating in blocks 2, 3, 4, 5, 6, 7, and 8. And then out here, we still have 50 more customers, and out here, we still have 50 more customers. Okay? But in terms of locations, they both, the beliefs, the thetas of the players are going to be restricted from the 2 to 8 interval, as are their own locations. Okay? So, what's the next step? Well, we're going to make a very similar argument that in this game, 2 and 8, this smaller game that survives the first round of iterated dominance, this smaller game, that 2 and 8 are going to be dominated by 3 and 7 respectively, in the same way that 1 and 9 were dominated before, right? So if you locate in block 2, if you believe the other player is located in block 2, and you locate in block 2, you're going to get half, right? So you can write this down. So if I believe that the other player locates in block 2, my utility of playing 2, given that belief, is equal to 225. Right? Whereas if instead I had located in block 3, she would have gotten all of block 1 and 2, and I get all of blocks 3 through 9. That's 7 blocks for me, which is $350, right? And that's better. So block 3 is better than block 2 under the belief that theta equals 2. If theta equals 3, the utility of block 2, given theta, is just the blocks 1 and 2 combined, so 2 times 50. Whereas the utility of block 3, I get to split everything, which is 225, which is better. 225 is better than 100. If I believe she locates at block 4, my utility of playing block 2 is now going to be block 1 and block 2 and half of block 3. So that's going to be 2 times 50 plus the half of block 3, which is 25, $125. Whereas the utility of choosing 3 under theta, so she chooses block 4, and I choose block 3, I'm going to get 1, 2, and 3. So I get 3 times 50, which is 150, which is better. And we can make the similar argument for theta 5, 6, 7, and 8. 3 is always going to be better than 2. So 3, let's say 2, is iteratively dominated by 3, and 8 is iteratively dominated by 7. Okay? So, of course, each player now decides they're not going to play blocks 1 or 2 or 8 or 9, but they're also aware, under common knowledge, that the other player doesn't as well. So it's as if they're facing a boardwalk of available locations that have block 3, 4, 5, 6, and 7. And of course, these 100 customers are still there, and these 100 customers are still there. But the locations that you think the other opponent is going to play and yourself are going to play are going to be restricted to 3 through 7. Iterative dominance is going to take out 3 and 7 with 4 and 6, the way we did before, right? So in the next round, we're going to be looking at just blocks 4, 5, and 6. 150 consumers on either side of those, and 4 and 6 are both going to be dominated by 5. If you'd like to see that, so I have to think about 3 beliefs that the other player that I can have about the other player. If I have belief theta equals 4, then my utility of choosing 4 is simply 225, of course, and my utility of choosing 5. I'm going to get block 5, 6, 7, 8, 9, and she'll get blocks 1 through 4. So I'm going to get 5 blocks. 5 times 50 is 250, right? And so locating in block 5 is better than locating in block 4 under the belief that she locates in block 4. If I think she's going to locate in block 5, my utility of 4, I'm going to get blocks 1 through 4. She'll get 5 through 9. So I'm going to get 4 blocks times 50, which is 200. The utility of block 5 is going to be splitting all the blocks, which is 225, and that's better. And finally, if my belief is theta equals 6, my utility of locating in 4 is equal to all of blocks 1 through 4 plus half of 5. So I'm going to get 4 times 50 plus half of that block 5. Which is 225, whereas if I had chosen 5 instead of 4, I'm going to get blocks 1 through 5, she's going to get blocks 6 through 9, so I'm going to get 5 times 50, which is equal to 250, which is better. Okay? So, 4 and 6 are iteratively dominated. Thus, 5 is the uniquely rationalizable location. Okay? So that's the rationalizable set of this location game, this boardwalk game, this hoteling model. In this very simplest case is the middle block, block number 5. Okay? So kind of thinking about more generalized idea of this model, for uniformly distributed consumers, if there are an odd number of blocks, the unique rationalizable outcome is the middle block. And if even, so if there's an even number of blocks, R equals the two middle blocks. For example, if there were 10 blocks, R equals the block number 5 and 6, okay? Because there would be 4 blocks to the left of 5, 4 blocks to the right of 6, and 5 and 6 represent the two middle blocks in that case. So it's rationalizable, which means that I can have beliefs that the other player locates on 5 and 6. If she locates in 5 and I locate in 5, we split all 10 blocks evenly. If she locates in 5 and I locate in 6, she gets all of blocks 1 through 5, I get all of blocks 6 or 9. In either case, I get exactly half the consumers. It just changes which half of the consumers do I get. Do I get half across all the blocks, or do I get exactly half of the blocks, right? So when there's an even number of blocks, there's 2 blocks that are equal. And then more generally than that, for other distributions, we locate where the median consumer is located. All right. So even if we had a distribution, a boardwalk distribution that looks something like there's a whole we have a pier on this end with a Ferris wheel and all kinds of food. So we have a ton of consumers over here, and then things kind of fizzle out at this end because it's all residential and not nearly so many people. So in a boardwalk game like that, we're going to both locate somewhere around the, here, where that is the median consumer. So we're always going to split half the customers is the basic idea, because if the other player is not located at the middle of that distribution of consumers, suppose he's located to the left of the median consumer. Well, I can locate just a tiny bit to his right, and I'm going to get more than half the consumers, and he's going to get less. If he had moved just to beside me, he would get half of all the consumers, which would be a better thing to do than stay where he was. And so we're always going to find that strategies that don't split the consumers in half are going to be dominated by something towards the middle. There's the block or the location immediately towards the middle from that particular location will always dominate that particular location. So there's always a tendency in this location game to locate in the middle of the consumers. So practical applications of this idea in terms of retail location. Think about 28th Street, 27th or 28th Street, between 6th and 7th Avenue in Manhattan. You have the Flower District, right? So there's a whole block, city block between the two avenues where there's nothing but flower stores. And they all locate on top of each other. And at first you might think it's strange that why don't they spread out? Why aren't these? Why aren't they all sort of trying to take consumers from different parts of the boardwalk? And there's an intuition that we see in this model where this advantage is to locating on the same location as your competitors. That's not always true. I mean, there are other types of competition that bring in other aspects, other strategic elements in which it's not optimal to locate on top of your consumers, on top of each other in relation to your consumers. But in this simple model, it is, and that would be kind of one practical application. Another application, you can think of location. You can think of applications where location is virtual, right? Location on a political spectrum. So imagine locating on a political spectrum of left and right, and wherever you locate, the people closest to you ideologically are going to vote for you. The people located ideologically closest to your competitor are going to vote for your competitor, right? And so from this, from the idea of locating on an ideological spectrum, we have what we call the median voter theorem. Which is that candidates always have to try to appeal to the median voter. So if you adopt a position that's too far to the left, your opponent adopts a position on the left but just to the right of you, and then that person takes all the voters to the right of that position, which is more than half the voters, and they automatically win the election, which means you didn't adopt that far left position, wasn't the optimal position in voting. So you should see a tendency of candidates to move to the middle. Now, of course, in more recent years, that's not what we've observed. We've observed a movement away from that. And so you have to enrich this model with more details to try to recover those kind of results that we see in the data. So it's not just locating on a left-right continuum. One thing you could do to extend the model is to make it multi-dimensional. So you're not just locating on left-right, or east-west, but north and south, right? So now there's two dimensions to a choice problem. You're locating on the plane instead of on a line segment. So that's one extension. You might also think of voters who only vote if someone locates close enough to them, but won't vote if somebody's further away. So you imagine you have, people on the left, people on the right, and imagine there's people here and people here who only vote if someone locates in that region. All right. So if they both move so if both candidates locate in the center, then the partisans don't vote at all. They just, the center is not appealing to them. They don't like people there, so they just stay home. If the partisans are big enough, like if we're out to here, and the partisans go out to here, right? Well, it's no longer going to be great for both candidates to stay at the center, because if someone stays at the center and someone moves to this partisan edge, that person can get all the partisans plus half the distance to the center, and now they're going to win the election because this person at the center takes this much plus this, and the partisan's going to take all of that, and the partisan's going to win the election. So now we have to think of different types of location options. It's very challenging to work those out as far as rationalizability. We're going to return to this model when we develop our Nash equilibrium concepts and think about partisans and what the underlying equilibrium location of this model is. And we can show that as the point at which the partisan segment is big enough that it actually destroys the median voter theorem, where you're no longer going to move to the middle, but you're going to want to appeal to the edge of the partisans. So you're going to want to adopt a position that's not too far to the left or too far to the right, but that will appeal to the partisans on the left and right. Anyway, so there's many ways that the location game has been extended. You can extend it to not just east and west, but north, south, east, west, or you can even go to a three-dimensional, 4 dimensions. Then once you get beyond 2 or 3 dimensions, it becomes mathematically almost impossible to solve the model, so most people just work on lower dimensional cases. of spatial location, and you can also think of like constraints on consumers won't go to you unless you're close enough to them. So we can think about those as two types of generalizations of this model. But the basic idea of the basic model is that the rationalizable location is to locate in the middle, and that's our summary of the location game from chapter 8.